The theory of cosmic inflation is a fundamental concept in physical cosmology that describes the exponential expansion of space in the early universe. This rapid expansion is believed to have occurred within a tiny fraction of a second after the Big Bang. Here's a detailed explanation. Overview. Cosmic inflation posits that the universe underwent a period of extremely rapid, exponential, expansion immediately following the Big Bang. This inflationary epoch lasted from about 1036 seconds to between 1033 and 1032 seconds after the Big Bang 1. Motivation. The theory was developed to explain several observed phenomena that the classical Big Bang theory could not, such as homogeneity, why the universe appears the same in all directions, isotropy. Flatness problem, why the universe seems to have a flat geometry on large scales. Horizon problem, why regions of space that are separated by vast distances have similar background radiation temperatures. Magnetic monopoles, the absence of magnetic monopoles, which should be abundant if the universe cooled from a hot, dense state without inflation. Mechanism. During inflation, a hypothetical field called the inflaton is thought to have caused this rapid expansion. Quantum fluctuations in the microscopic inflationary region were magnified to cosmic size, becoming the seeds for the growth of structure in the universe. 1. Theoretical status. The basic inflationary paradigm is widely accepted by physicists, as it has made several predictions that have been confirmed by observations. However, the detailed particle physics mechanism responsible for inflation is still unknown, and there is a minority of scientists who dissent from this position. 1. Implications. Inflation theory has profound implications for our understanding of the universe. It suggests that the large-scale structure we observe today originated from quantum fluctuations during the inflationary period. It also implies that our observable universe is just a small part of a much larger and possibly still inflating cosmos. Current research. Physicists continue to explore the theory of cosmic inflation, seeking to understand the precise conditions that led to it and its implications for the evolution of the universe. Experiments and observations, such as measurements of the cosmic microwave background radiation, are crucial for testing the predictions of inflation theory and refining our understanding of the early universe. 1. In summary, cosmic inflation is a pivotal theory that has reshaped our understanding of the universe's birth and its subsequent evolution. It provides a framework for explaining the uniformity and structure of the cosmos and continues to be a central topic of research in cosmology. Cosmic inflation and dark energy are both concepts that describe periods of accelerated expansion in the universe, but they occur at vastly different times and scales. Cosmic inflation occurred immediately after the Big Bang, lasting from about 1036 to 1032 seconds, caused by a hypothetical field known as the inflaton field. Resulted in the exponential expansion of space, solving the horizon and flatness problems and providing the seeds for the large-scale structure of the universe. Dark energy is the force driving the current acceleration of the universe's expansion. It's a mysterious form of energy that makes up about 68% of the universe today. Unlike inflation, dark energy's effects are relatively gentle and ongoing. The relation. While cosmic inflation and dark energy are not the same, they may be related in the sense that they both cause the universe to expand at an accelerated rate. Some theories suggest that the same field responsible for inflation, the inflaton field, could also be responsible for dark energy, but in a much weaker and slower form. 1. This idea is known as quintessence, where an evolving scalar field is responsible for the late-time accelerated expansion of the universe. 1. Another perspective is that dark energy and the inflaton field are different manifestations of fields that drive the universe's expansion at different epochs. For example, the quintessential inflation model posits that the same field is responsible for both the early inflationary period and the current acceleration due to dark energy, although this requires a fine-tuning of the field's potential energy function. 1. In summary, while cosmic inflation and dark energy are distinct phenomena, they may be interconnected through theoretical models that describe the universe's expansion, and ongoing research continues to explore these fascinating concepts. Quintessence and the cosmological constant are two theoretical concepts proposed to explain the accelerated expansion of the universe, but they have distinct characteristics. Cosmological constant, \lambda, introduced by Einstein as a modification to his general theory of relativity, represents a constant energy density filling space homogeneously, has a fixed equation of state with a pressure, P, that is negative and equal in magnitude to its energy density, \rho, giving it an equation of state, W equals P \rho equals -1. does not evolve with time. It is a static form of dark energy. Quintessence, a dynamic, evolving field, often modeled as a scalar field similar to the inflaton field from cosmic inflation, has a variable equation of state, where W can vary over time and is typically greater than -1. Can lead to different observational consequences, such as variations in the acceleration rate of the universe over time. May also be spatially inhomogeneous, leading to variations in the density of dark energy in different regions of the universe. In essence, the key difference is that the cosmological constant is a static form of dark energy with a fixed equation of state, while quintessence is a dynamic form that can change over time and space. 11. This distinction is crucial for cosmologists when comparing theoretical predictions with observational data to understand the nature of dark energy. Quintessence, as a dynamic form of dark energy, can have significant effects on cosmic structure formation. Here's how it can influence the process. Influence on dark matter clustering. Quintessence models can lead to different dark matter (DM) clustering patterns compared to the standard lambda-cold dark matter (CDM) model. This is due to the variation in the equation of state of quintessence and its impact on the expansion rate of the universe. N-body simulations have shown that quintessence can result in a large-scale distribution of DM that differs from CDM predictions. 1. Effect on cluster mass function. The mass function of clusters, which describes the number density of clusters as a function of mass, can be altered by quintessence. The changes in the equation of state and the cosmological parameters can lead to variations in the abundance and distribution of galaxy clusters. 1. Impact on halo internal velocities. Quintessence can affect the internal velocities within halos, potentially leading to observable differences in the dynamics of galaxies and clusters of galaxies. 1. Growth of matter perturbations. The growth rate of matter perturbations, which are the seeds of cosmic structures such as galaxies and clusters, can be slowed down by the presence of quintessence. This is because the accelerated expansion it causes can hinder the gravitational collapse necessary for structure formation. 2. Spectrum of fluctuations. Quintessence generally leads to a less powered spectrum of fluctuations than CDM, which can result in a 20% more efficient structure formation process on small scales compared to CDM. 3. In summary, quintessence can have a variety of impacts on cosmic structure formation, from altering the clustering of dark matter to changing the internal dynamics of galaxy clusters. These effects are crucial for understanding the evolution of the universe and are a key focus of observational cosmology. The mathematical foundations of cosmic inflation are rooted in the theory of general relativity and quantum field theory. Here's a detailed look at the key concepts: general relativity and the Friedmann equations. Cosmic inflation is described within the framework of Einstein's general relativity. The dynamics of the universe are governed by the Friedmann equations, which are derived from the Einstein field equations. These equations describe how the expansion rate of the universe, the Hubble parameter, h, changes with time due to the energy content of the universe. Scalar fields and the inflaton. Inflation is driven by a hypothetical scalar field called the inflaton. The dynamics of this field are described by the Klein-Gordon equation in an expanding universe. The potential energy, the \phi of the inflaton field, \phi dominates the energy density of the universe during inflation, leading to exponential expansion. The slow roll approximation. To sustain inflation for a sufficient amount of time, the inflaton field must roll slowly down its potential. This is quantified by the slow roll parameters \epsilon and \eta, which are small during inflation. They are defined as equals 2 mpl2 v phi v phi 2, eta equals mpl2 v phi v phi, where m_text pl is the reduced Planck mass, and primes denote derivatives with respect to \phi. Quantum fluctuations. Quantum fluctuations of the inflaton field lead to the generation of density perturbations. These perturbations are stretched to macroscopic scales by the inflationary expansion and become the seeds for structure formation in the universe. The power spectrum of these perturbations is nearly scale invariant, which is a key prediction of inflation. End of inflation and reheating. Inflation ends when the slow roll conditions are violated, typically when \epsilon becomes of order 1. The universe then transitions into a hot, dense state in a process called reheating. The inflaton field decays into standard particles, and the universe begins the standard hot Big Bang evolution. Predictions and observations. The mathematical framework of inflation makes several predictions that can be tested observationally, such as the flatness of the universe, the absence of magnetic monopoles, and the specific characteristics of the cosmic microwave background radiation. These mathematical foundations are supported by a wealth of observational data, including measurements of the cosmic microwave background, large-scale structure, and other cosmological observations. While the exact nature of the inflaton field and its potential remains a topic of research, the mathematical framework provides a robust basis for understanding the early universe's rapid expansion. Cosmic inflation is closely related to primordial gravitational waves, as the rapid expansion during inflation is the rise to produce these waves. Here's how they are connected. Primordial gravitational waves. These are ripples in the fabric of spacetime that were generated in the early universe. According to inflation theory, these waves were produced by the quantum fluctuations of the inflaton field that drove inflation. They are considered to be the first gravitational waves ever produced, dating back to a fraction of a second after the Big Bang. Relation to cosmic inflation. During inflation, the exponential expansion of space amplified these quantum fluctuations, stretching them to macroscopic scales. This process not only created the density perturbations that led to the formation of galaxies and large-scale structures but also generated gravitational waves. These primordial gravitational waves are the rise to leave a distinct imprint on the cosmic microwave background (CMB) radiation, specifically in its polarization pattern. Observational evidence. Experiments like BICEP 2 have sought to detect these imprints in the CMB as a B-mode polarization pattern, which is a unique signature of gravitational waves 1. The detection of such patterns would provide strong evidence for the theory of inflation and help us understand the conditions of the early universe. In summary, primordial gravitational waves are a fundamental prediction of cosmic inflation, and their detection would be a major milestone in cosmology, confirming our ideas about the very early universe and the physics governing its expansion. Observations of the cosmic microwave background (CMB). The CMB provides a wealth of information about the early universe. Inflation predicts specific patterns in the temperature fluctuations and polarization of the CMB that can be tested with precise measurements. 1. Large-scale structure of the universe. Inflation theory predicts the initial conditions that led to the formation of galaxies and large-scale structures. Observations of the distribution of galaxies and the cosmic web can test these predictions. 1. Spectral index (NS) and tensor-to-scalar ratio registered trademark symbol. Inflation predicts a nearly scale-invariant spectrum of primordial density fluctuations, characterized by the spectral index (NS). It also predicts a certain level of gravitational waves, quantified by the tensor-to-scalar ratio, R. Current surveys constrain these parameters, allowing us to test specific inflationary models. 1. Non-Gaussianity. Inflation generally predicts that the primordial fluctuations should be Gaussian. However, some models predict slight deviations from Gaussianity. These non-Gaussian features can be searched for in the CMB and large-scale structure data. 2. Consistency relations. Inflationary models predict certain relationships between observable quantities like the spectral index and its running, and the tensor-to-scalar ratio. These consistency relations can be tested with observational data. 2. Quantum fluctuations. Inflation stretches quantum fluctuations to cosmic scales. The statistical properties of these fluctuations can be tested against observations of the CMB and the large-scale structure. 3. Reheating temperature. After inflation ends, the universe reheats. The temperature of reheating can leave imprints on the distribution of matter and radiation that can be tested with cosmological observations. 4. These methods collectively provide a robust framework for testing the predictions of cosmic inflation and refining our understanding of the early universe. Cosmic inflation, dark matter, and dark energy are all integral components of our current understanding of the universe, each playing a distinct role in its evolution. Cosmic inflation refers to the exponential expansion of space that occurred a fraction of a second after the Big Bang. It set the initial conditions for the universe, including the distribution of energy that would eventually lead to the formation of galaxies and other structures. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to current detection methods. It is believed to constitute about 27% of the universe's mass energy content. Dark matter's gravitational effects influence the formation and rotation of galaxies, playing a crucial role in cosmic structure formation. Dark energy is a mysterious force that is causing the acceleration of the universe's expansion at present times. It accounts for approximately 68% of the total energy content of the universe. The nature of dark energy is one of the biggest mysteries in science, often associated with the cosmological constant \lambda in Einstein's field equations. The relation, cosmic inflation, is thought to have created the initial quantum fluctuations that would become the seeds for all structure in the universe, including dark matter. The same quantum field theory that predicts inflation also suggests the existence of particles that could be candidates for dark matter. Dark energy, while not directly related to the mechanisms of inflation, is another form of energy that affects the universe's expansion. Some theories propose that the same type of field responsible for inflation could be related to dark energy 11. In summary, cosmic inflation laid down the early universe's structure, dark matter shaped the formation of that structure, and dark energy is currently influencing the expansion of space. Understanding the relationship between these three concepts is key to unraveling the history and fate of the universe. The inflaton field is a hypothetical scalar field that is central to the theory of cosmic inflation in cosmology. Here's a detailed explanation of what it is and its role in the universe. Conceptual overview: the inflaton field is conjectured to have driven the rapid exponential expansion of the universe during the inflationary epoch, which occurred a fraction of a second after the Big Bang. It is a quantum field, similar to other fields in particle physics but with unique properties that allowed it to dominate the energy density of the early universe. Role in cosmic inflation: the inflaton field had a high potential energy during the inflationary period. This energy acted as a repulsive force, causing space itself to expand at an accelerating rate. The field slowly rolled down its potential energy curve, a process that is described by the slow roll approximation in inflationary models. Mechanism: as the inflaton field decayed to a lower energy state, it triggered a phase transition from a false vacuum, a metastable state with high energy, to a true vacuum, the lowest energy state. This phase transition is what ended the inflationary period and began the reheating phase, where the energy of the inflaton field was converted into particles that make up the matter in the universe today. Field quanta: the quantum fluctuations of the inflaton field were stretched to cosmic scales by the inflationary expansion. These fluctuations became the seeds for the large-scale structure of the universe, such as galaxies and clusters of galaxies. Mathematical description: in the context of field theory, the inflaton field is described by a Lagrangian density that includes a kinetic term and a potential term. The dynamics of the field are governed by the Klein-Gordon equation in a curved spacetime background. Current status: while the inflaton field is a theoretical construct, it is a crucial element of the inflationary model, which has been successful in explaining many observed features of the universe. The exact nature of the inflaton field, including its potential energy function and its interactions with other fields, is still a subject of active research in theoretical physics. In summary, the inflaton field is a theoretical entity postulated to explain the very early universe's rapid expansion. Its properties and behavior during the inflationary epoch set the initial conditions for the development of the universe as we observe it today. There are several alternative theories to cosmic inflation that attempt to explain the dynamics of the early universe without invoking an inflaton field. Here are a few of the notable ones: ekpyrotic and cyclic models. These models propose that the universe underwent a series of cycles of expansion and contraction. The ekpyrotic model, in particular, suggests that the large-scale structure of the universe was created by the collision of brands in higher dimensional space. 1. String gas cosmology. Based on string theory, this model suggests that the universe began with a hot, dense state of strings. As the universe expanded, strings that wrapped around compact dimensions could have led to the formation of galaxies. 1. Matter bounce scenario. This scenario posits that the universe began with a contracting phase that led to a big bounce rather than a big bang. The bounce could have created conditions similar to those predicted by inflationary models. 1. Quantum cosmology models. These models use principles from quantum mechanics to describe the early universe. They often involve a wave function for the universe and do not require a classical inflaton field. 1. Variable speed of light, VSL theories. VSL theories propose that the speed of light was much higher in the early universe, which could account for the horizon problem that inflation is meant to solve. 1. It's important to note that while these theories provide interesting alternatives to inflation, none have yet achieved the same level of observational support as the inflationary model. The debate and research continue as scientists seek to understand the true nature of the early universe's dynamics. Studies and discussions in the scientific community that explore non-inflationary scenarios of the early universe. While specific experimental setups targeting these alternatives may not be as prominent as those searching for evidence of inflation, such as the BICEP and Planck missions, researchers are considering observations that could challenge or offer alternatives to the inflationary paradigm. For instance, some studies focus on unique galactic phenomena that could be explained by non-inflationary cosmology, such as galaxies with reverse rotating disks. 1. These observations could potentially provide insights into different cosmological models that do not rely on inflation. Additionally, theoretical work continues to propose and refine models that could be tested against astronomical observations. For example, the ekpyrotic and cyclic models predict specific signatures in the cosmic microwave background and the large-scale structure of the universe that differ from those predicted by inflationary models too. While direct experiments may not be as common for non-inflationary scenarios, the field is active with theoretical work, and observational data continues to be scrutinized for evidence that could support or refute these alternative theories. The theory of cosmic inflation was proposed by American physicist Alan Guth in 19811. Guth developed the idea while working at MIT, and his theory has since become a cornerstone of modern cosmological thought. The theory was further developed by other physicists, notably Andrei Lindy and Alexei Starobinsky, who have also made significant contributions to the field. 23. Guth's theory addressed several issues with the Big Bang model, such as the horizon and flatness problems, by suggesting that the universe underwent a period of rapid exponential expansion shortly after the Big Bang. This expansion smoothed out any irregularities and inhomogeneities, leading to the remarkably uniform universe we observe today. For their pioneering work on cosmic inflation, Guth, Lindy, and Starobinsky were awarded the 2014 Kavli Prize in Astrophysics too. Their contributions have provided a deeper understanding of the early universe and have had a profound impact on the field of cosmology. Alan Guth was motivated to propose the theory of cosmic inflation to address several major puzzles in the standard Big Bang cosmology that were unresolved at the time. Here are the key motivations behind his groundbreaking idea: horizon problem. The universe appears remarkably uniform in all directions, isotropic, even in regions that should not have had enough time to exchange information or energy to reach this uniform state. This is known as the horizon problem. Flatness problem. Observations suggest that the universe is very close to being flat. However, according to the standard Big Bang model, any initial curvature would have become more pronounced as the universe expanded, which is not what we observe. Magnetic monopoles. Grand unified theories, GUTS, predict the existence of magnetic monopoles, but none have been observed. Inflation dilutes the density of such exotic particles, explaining their absence. Structure formation. The origin of the large-scale structure of the universe, such as galaxies and clusters of galaxies, needed an explanation. Inflation provides a mechanism for the generation of the initial density perturbations from quantum fluctuations. Guth's theory of cosmic inflation proposed that a brief period of exponential expansion in the early universe could solve these problems by smoothing out any inhomogeneities and anisotropies, leading to the observed large-scale uniformity and flatness. 11. Additionally, it would dilute any unwanted relics like magnetic monopoles and provide the seeds for the formation of cosmic structure. 33. This theory has since become a cornerstone of modern cosmological thought and has been supported by various observations, particularly those related to the cosmic microwave background radiation. That was all. Goodbye.